Hello, everyone. Welcome to Lattice Developer Conference. We will be presenting today about optimized ML solution with Lattice FPGA. It's also known by name sensAI. So let's get started. So uh, we had two speakers on this presentation. Myself, I'm Shripad Hegde. I'm leading the team that is responsible to deliver the ML solutions and CI from Lattice. We provide a low power solution for edge AI ML. Right. So I'm leading this team since its launch in 2018, and I'm happy to introduce some of the work we have done to enable the edge AI. So along with me, I have Rakesh Nakod, who is an associate principal engineer from Softnotics, which got acquired by Moschip recently, and it's part of Moschip now. And he has an in-depth experience on AI, ML, and deep learning area from last 10 plus years, including both vision as well as natural language processing and other areas. So he'll be talking about one of the use case Softnotics did using our solution, which is around the barcode detection and reading. So he will cover today barcode detection in depth and how he basically enabled this application on our solution. So with that, let's move on and get started. And this is the agenda for today's presentation. First, I'll be introducing about sensAI solution stack and what all different options available, and how flexible is our solution for developing various application and things like that. So one of the key aspect is the design methodology and the tools for the AI ML area. So we will be covering the robust tool and methodology that we have developed to ease the use of our solution. That is one of the key thing. And then basically Rakesh will be talking about the case study that I mentioned earlier. Feel free to ask any question on how easy it is to use our solution and things like that to Rakesh. He will be able to give you very good insight into the solution from a user perspective, while I'll be providing more insight from our capability perspective. Right, and at the end we will cover this. We will have also the demo. Rakesh will go over a demo of barcode detection, and then we will go over the summary. Right? So now, sensAI, which got launched in 2018, basically is a solution stack. Lattice provides multiple solution stack. When we talk about solution stack, we take the layered approach. We provide like end-to-end solution that is required to develop uh, but enable a particular technology. For example, in this approach, we have provided like Lattice provides multiple families of FPGA, low power FPGAs. Some of the families I have mentioned here, like Avant is the most recent version. We have Certus Pro and Crosslink that are well tuned for video application and IO. Aggregation and things like that, which are very popular in many of the market segment, including consumer, automotive, as well as many of the applications. We enable our AI ML on top of all these devices that are kind of a thing. And then our approach is basically a soft IP core, which is laid on top of the FPGA. Like it's an overlay technology kind of a thing, which accelerates basically neural network inferencing. So those who are familiar with neural network, there are two steps. One is the training step, and another is the inferencing step. So what we enable is the inferencing on low power devices, on FPGA devices. Right. So, and the third one is again the software tools and basically the methodology, how we enable the easy adoption and things like that. One of the concept basically thing that we focus is how to make this whole thing software friendly, like mainly from the ML user perspective, so that hiding all the details about the hardware implementation and things like that, that is one of the key aspect we keep in mind when we develop the tools and provide the solution. So on top of that, we have developed a model zoo that basically hosts many of our reference designs, and basically shows how to kind of address different areas, application areas, or how to create the neural network, train the neural network, what type of operators will be very efficient for inferencing on FPGA and things like that. That is the next layer that we provide. And also we kind of enable many customer designs with pointed services, particularly on some of the areas that is mentioned here. So basically, the key aspect of the whole solution is it's very flexible, right? So that's the key aspect when we talk about AI ML solution. So it is flexible in multiple ways. First is like we provide multiple ML engines which are that are configurable. Basically targeting different requirement. You can make it very compact and fit other application, other video or application on top of it, kind of thing. Or you can have a very enhanced engine that consumes a lot of resource and things like that, but gives a higher performance, kind of thing. So it is scalable, right? The whole engine is scalable. That is the good thing about when you implement it on the FPGA device. So then we have a user-friendly design tools. That is again, there are multiple suites. One is basically enabling the designing kind of a thing, or the training aspect. sensAI Studio, I'll touch a little bit upon that. And then we have a sensAI compiler that basically targets runtime generation, basically targeting compilation of the neural network for the inferencing purpose, right? So that's sensAI compiler. And then we have basically reference designs and models, as I mentioned earlier. uh, uh, Reference design is not just about the trained model. Of course, we provide a lot of trained model that can be used for transfer learning and creating a different applications using those models. At the same time, it also provides a reference design integrating with other IP cores like RISC-V and things like that to enable a design pipeline. Even the video processing pipelines and things like that are provided as part of a reference design. Then basically we have support on small and mid-size low power FPGA. Basically, we provide uh, various options in terms of the device that you can target. So now, next few slides, I'll be touching upon the options that are available in terms of the IP core, basically the engine, ML engine, right? So, and like the reason why I'm touching upon this in couple of slides is basically it shows how flexible is our solution, targeting even a very small device to a mid-size FPGA device that we shape, and how basically it impacts kind of a thing. I will be presenting our CNN IP accelerator that basically comes in various flavors, and the reason why we provide different versions of CNN IP, because it meets a different target requirement application creation. You can basically do a trade-off between the performance versus the resource utilization. Particularly being an FPGA, you can put a lot of other application around this CNN IP, like video aggregation, or ISP kind of functions and things like that. Or you can go with a larger engine which basically targets higher performance and things like that. So it's a trade-off that basically allowed with these different flavors of the IP. So here what I'm showing is the basic architecture of the basic CNN plus IP. As you can see, we have different blocks here, or we can call it as engines, that basically enables certain operations in the neural network. Right, so it's basically the convolution is the main operation that takes most of the execution time during the inferencing. So we have kind of an engine that accelerates convolution, fully connected layers, as well as there are like non-linear functions, as well as standard operations like max pooling and those kind of things. We kind of accelerate, and the main thing that gives the advantage is the on-chip memory in FPGA, right? So we have different types of on-chip memories on our FPGAs, and the way we kind of architect it gives a very good advantage in terms of performance, in terms of power management, and those kind of things. It becomes very efficient, right? So that's why this is well tuned. This architecture is well tuned towards our FPGA device. So here, like again, this architecture, the base architecture is good on many application like human detection and things like that, which are being implemented on crosslink NX. User can implement any kind of a detection problem and things like that with this engine, which is on a very small low power FPGA, which will be very cost effective also. And this is well tuned for like 8-bit data kind of a thing. So that's kind of application that needs to be targeted with this particular IP. Now we have a CNN plus optimized engine. As you can see from the previous one, the main the enhancement here is the multiple cores that are used to accelerate the convolution operations, right? So instead of just consuming one input and producing one output, here basically we can consume multiple input, and multiple output can be produced at the same time, and that again gives quite a bit of performance enhancement compared to the previous one. Of course, this engine works on the crosslink NX device also that was targeted earlier. So but it consumes most of the resources available on that device, and user will be tied with only CNN operations. If you target a slightly larger device, Certus Pro NX, basically still you will have a lot of rooms to implement other logic or functionality on top of this IP, right? So that's a kind of a trade-off that you need to think while choosing between the two engine, right? So performance versus what is the area, and what is the power, and what is the performance benefit that you are getting, right? So again, here we can implement a human detection, of course, with a higher frame rate and things like that. And so ROI based, like this is a region of interest, ROI here stand for. So based attention tracking and user identification, onlooker detection, these kind of applications are enabled on top of this, right? So as available as a reference designs or a demo that user can use as a starting point, right? So now, then again, we have a extended engine. Basically, like why I'm talking about all this engine is again to showcase the flexibility, right? So, for example, when we do certain application like segmentation, right, it requires a special operations like unpooling, diluted convolutions, and argmax. So some of the things are specific to only certain application or certain network type, not necessarily implement necessary for other things. So if you have just one architecture, then basically all those resources, or there will be a overhead penalty. So that's why what we do is basically we customize the engine so that it is good for certain target application and target network type. So this is the one such example where it is good for background segmentation application, which certain special operations like argmax and those kind of enhancement that are required, right? So in this engine. Similarly, this is with more advanced version where we make it more generic in terms of operation. As you can see, earlier engines were targeted for certain specific operations and things like that. Now, let's say you want an engine that is capable of handling more generic operations in terms of bitwise operations and things like that, like the pixel level operation and things like that. We have advanced CNN IP because now we include a vector ALU, and vector ALU is a very generic one that provides bitwise or element-wise operations. Even sometimes you can refer as pixel level operations, and that provides a lot of flexibility and things like that, right? So the barcode detection that Rakesh is going to talk is basically built on top of this advanced CNN IP, right? So that's we will look at the use case at later point. So now again, on top of the engines that we talked earlier, any of this engine can be integrated with our RISC-V ecosystem, right? So RISC-V, basically, there are two ways to use the RISC-V. We in certain application we use the RISC-V just as a control path for a control path operation, while all the data manipulation is happening inside the CNN IP, because CNN IP can operate on its own. It does not require any processor. It's not like a co-processor architecture kind of a thing. It is on its own. It can do all the operations, or it can implement the application. But we can introduce the RISC-V to enable more of a control path, basically managing the data movement from the camera modules and things like that, or doing some scalar and operations and things like that, right? That's one way of using the RISC-V. Another way is if you can use only this, for example, the convolution engine from the previous one, and implement other operations on the RISC-V, because like there are applications like predictive maintenance that are like a background application. Runtime is not so important while doing the inferencing. In such application, what we can do is you can offload all the operations onto RISC-V and use only certain accelerations like convolution with a dedicated engine. That's another way of using this thing. We provide both the solutions around the RISC-V. So now, switching the gear from engine perspective to the design methodology, tools are very important to enable the design and application creation. As I mentioned, so we have already created these engines, and user need not have to know a lot of details about these engines. It's already kind of hidden by providing this design methodology. So user needs to understand the design methodology, which is more software oriented, rather than going into the nuance of basically our engines, right? So the model, basically the design methodology, we have a integrated design environment called sensAI Studio. It integrates both the training aspect as well as the runtime generation, that's compilation of neural network. It integrates both of them, right? And also the model zoo that we kept on talking about, all these reference designs are integrated with this design environment. The model Zeus itself is available on the GitHub, and it is integrated, right? So, and the data also, it can be hosted on the local GPU machines, or it can be cloud hosted. So it's basically an integrated environment. On the other hand, user, if they have already a robust training framework and a methodology, they can just use our neural network compiler. It comes as a standalone GUI tool, which is easy to use, and so that they don't have to alter their existing neural network training and those practices that are already in the use, right? So that both the options are available. So again, here is basically some of the models that we support, and some of the things that are enabled currently. There is always we keep adding more support and kind of a thing, but at the same time we don't try to make it very generic solution, because it loses that optimization or like a targeted application like advantage with that, right? So we keep still this one as very kind of a tightly coupled and tightly integrated solution, targeting video applications and what is needed for certain edge applications around the video and things like that. But at the same time, we have already enabled many of the audio applications and like a key phrase detection and things like that. When it is integrated with the video application, it makes a lot of sense. When the two different sensors applications are integrated, it brings more value into the application creation, right? So here is some of the information regarding basically what we support as of today, right? So now, in terms of the model training, again, one of the key important thing is like we have provided the models and the transfer learning capability, as well as the data, even the basic data labeling capability. All those things are available, but it's not a mandatory tool, right? So model training can happen outside of our this environment. And The key aspect is, after training the model, either in TensorFlow, Keras, or some of these framework, basically user needs to freeze the model and for inferencing purpose. This is very common practice in any of the neural network inferencing on the edge devices, on the resource constrained device, right? So that's basically what we need to do in terms of and then basically pass it to the neural network compiler. So one of the key aspect in the methodology is the quantization, right? So quantization is very important because we are talking here about embedded device, or a small devices for a neural network inferencing, which are, most of the application works with 8-bit quantized data and the weights today. Now, what we found is the quantization, instead of doing a post training quantization, it is better to do the quantization during the training. That gives a better accuracy and better results. So though we support both post training quantization as well as quantization aware training support, our recommendation is to use the quantization aware training. And again, in the quantization aware training, there are different techniques. So we provide basic APIs, or the layers and things like that can be used basically during the neural network training to enable the quantization, right? So, and there are two different approaches. One is keeping the step size for the quantization fixed. Those who are already working on the neural network quantization easily understand this concept of the step size in the quantization. We One way is to keep that as fixed. Another way is even we can learn the step size also, right? So we provide even the APIs and the capability to learn those step size. So some more work is in progress around this concept, and anticipate more advancement in this area, because we are seeing some good progress as we go into even a smaller data weight like 4-bit and things like that. This becomes more and more critical and useful to get a better accuracy, right? So keep tuned for further enhancement around the quantization, but even today it is a very critical step in the overall flow. Now, the next important aspect is the compilation, right? So the compilation is basically the one that generates the runtime for our FPGA or the neural network, right? So the why I'm talking about the compiler is, compiler basically comes with its own GUI, and the reason why we provide GUI is basically it's very easy to use. Like those who are not very familiar with rest of the flow, because in an organization there are multiple teams working on different aspect. The team that is training the neural network may be different than the team that is doing the inferencing on the FPGA and things like that. So, or the same during the evaluation, same person may be doing both the activities, right? So we have to consider all the different user group and see what is the best thing for them, right? And we thought this is the best way if we provide a GUI based tool that is easy to install and configure and kind of generate for various options that we provide in the engine and things like that. Then that is the right way to go about it, right? So that's why we provided a GUI enabled tool where user can do various configuration and selections and generate the runtime, right? So it also provides a lot of other functionalities like hardware debug capability, simulation, because even without having the hardware board or anything like that, you can check the performance as well as the accuracy of the model that you are targeting for inferencing and things like that. So all these things capabilities are inbuilt within the compiler tool, right? So this is the one of the best practice is to basically train the initial model and take it through the compiler and see how basically the compiler, so it basically gives you all kinds of analysis report, and based on that keep tuning. So keep this one like a compiler or a tool in the loop, right? So in the entire process of training and inferencing of the model, don't take this one as a last step wherein basically I'm done with all the training and now I have the best model with a good accuracy, let's go and do the inferencing. That's not a very good design methodology. So design methodology is basically, it has to be more iterative, involving the compiler and getting the feedback back to that training and things like that, right? So that's a good practice. Now, with that, I like to pass it to Rakesh to walk through one of the application that he developed basically around the barcode detection, and give us more insight how he was able to successfully use all these capabilities and get the application done, kind of a thing. Rakesh, over to you.
Yeah, thanks, Shiva. Thank you, Shiva. Well, hello, everyone. My name is Rakesh Nakor. As Shiva introduced, I am working as an associate principal engineer with Softnautics, which is a Moship company, and I'll be taking you the use cases for barcode detection that we built using the sensAI stack. Now, before we move on to the use case, let me give you a quick introduction of my organization. So we are a semiconductor and embedded AI solutions company that recently got acquired by Moship. We are primarily focused on VLSI design and verification, embedded AI and IoT solutions, mixed signal IPs, and turnkey ASICs. We command a strength of 1400 plus engineers, which are spread across Silicon Valley, USA, as well as we have multiple locations in India, like namely Hyderabad, Bangalore, Pune, and Ahmedabad. Now, regarding our association with Lattice, so we are actually custom design service partner for Lattice for more than 5 years, and we are actively engaged in designing reference design and basically development of the NN compilers for sensAI. And this association has been very good. And yeah, so with that, let's quickly move on to our case study, which is the barcode detection. Yeah. So as you everyone knows that what a barcode detection is basically an application where okay we have a everyone is aware of a barcode reader scanner which you pass barcode on and it actually reads the values from the barcode. Now, though it looks a very simple case of handheld devices and some tabletop setups reading the barcode, they actually don't work. They can do much more work when we actually club them with AI. So our objective over here is to enable the barcode detection to do more than what they are right now doing. So what is that more? So the barcodes are actually having a lot of versatility across industries in terms of size, and even there are different types of barcodes that spread across different geolocations. These barcode scanners basically read one barcode at a time, but what we want to unlock is detect and read multiple barcodes. We also want to read barcodes that are distorted, damaged, or skewed. And we also want to detect and read barcodes that are actually in motion. Now, all these things are not possible with the current devices that we see across, but yeah, definitely with the potential of AI, will actually enable this. And our case study is actually a step towards enabling this possibility. So let's go through a quick solution overview. So basically, following a typical machine learning pipeline that most of the people or AI engineers are aware, you basically require a data set. Now, with this, you collect data set from the internet, you generate your own, you generate your augmented set. So basically, you need to have a data set. Now, once you have the data set, the next step is you actually train your AI architecture or algorithm using this data set. Now, this training will actually give you a model file. In our terminology, model file is actually the AI algorithm which is trained on a data set. And this file is actually what we'll be using further for creating an application. Now, depending upon the architecture that you use, like TensorFlow or Keras, you will actually have to freeze that model file post training and you will be actually getting a frozen file format. So if you are using TensorFlow, basically you will end up having a .pb file as an extension, and if you are using Keras, then it will be .h file. Now, once you have this trained model file at your disposal, you have to run them through our Lattice sensAI and then compiler. Now, the job of the compiler, as mentioned previously by Shripad, is actually to convert your trained AI models into compatible AI models that will run on our Lattice hardware. Now, these models are carrying extension .mcs file. Okay, so once the compiler's output for a given PB or H5 file will be an MCS file, and this MCS file you will be actually flashing it on a Lattice board. Now here we'll be actually deploying it on a Certus Pro NX board. You will actually need an RTL inference pipeline to execute this MCS file. Now most of our reference designs or models do come with the RTL inference pipeline, so that thing is mostly taken care of. You just need to pick an appropriate reference design. You will get the corresponding RTL pipeline for that design. And once you have the RTL pipeline, you flash this MCS file onto the device, just connect it to a camera or an application, and yeah, now you put any box or barcode in front of it, it will start detecting the barcode. Now, this is like a very rough solution overview of typical, but now let's get into detail like how we actually end up building this solution. So, going on to the next slide, if you see, I have segregated processes of how to build the solution using sensAI stack. So this is like a high level overview of the process that we follow for building the solution. So this is staged into different sections. So first is the reference model. Then we go through data engineering. Then we have model training, compilation, testing, and deployment. Now, this is the things inside. These are actually steps that we follow at different stages. We'll go into detail of them one by one, and at the same time, I will cover like what we did actually for barcode detection at these stages. Okay, so first stage is reference model. Now, before you actually start building an AI solution for any problem statement given, you must be able to frame the problem properly. Now, framing ML problem is actually important. For example, if you are building an application that needs to do classification of cars, maybe like you want to differentiate whether a given car picture is of a sedan or a SUV or a hatchback. Now, when you are talking about this problem statement, in our terms, we call it as a classification problem. So similarly, when you look at detecting a barcode, which is like identifying a barcode in a given image and identifying the coordinates so that you are actually able to draw a bounding box. This problem statement is actually called as object detection problem statement. Okay. Now this problem statement identification and framing of your problem statement is actually necessary because that will help you allow to select appropriate reference design from the model zoo. Okay. Now we have multiple object detection models. As you saw earlier, we have multiple algorithms, and these algorithms are spread across multiple problem statements. So once you are able to frame your problem, you can choose appropriate model from the zoo. Now, choosing the appropriate model is also important because the architecture that they are supported is actually compatible with the Lattice hardware and NN compiler. So this will actually give you a good head start so that you don't have to worry about, okay, after building a model of my own, whether it will run through compiler or not. You don't have to worry. Once you choose an appropriate model, the success rate of your application running through the compiler and successful getting deployed is close to 100%. Now, for our problem statement, we start, we sorry, for our problem statement, we chose to start off with two models basically. One is mobile net. This model we chose because this is a very small model and it was popular for limited computed devices. And the other one we chose was YOLO V5 because YOLO architecture is one of the state of the art models for object detection. Now, other than the algorithms that you choose, okay, you can also choose the variants for this algorithm because there are a couple of variants also available in the reference models. Now, these variants are basically depending upon the resolution. They are also depending upon the framework that you want to use. So now what we selected for our problem statement was two variants for mobile net. One was VGA, which is a 640 by 480 resolution, and the other one is QVGA, which is 320 by 240. And for YOLO, we actually selected a smaller resolution, 320 by 240, and we actually happened to build a custom resolution of 160 by 160. So going ahead with this selection, we tried to build a this reference model. We tried to build a solution. So going on to the next step, important one is actually data engineering. Now, once you have the algorithm, the model design, and the appropriate reference model with you, the so you need to add actually fuel to those algorithms. So data set is the fuel for any AI algorithm. And now for our application, we actually had to go ahead and select research more of open source data sets. Like we went across Earthay Labs, RuboFlow. These are a few of the data sets that we use. And these data sets that we scanned and we uh, collected, they formed a base 5,000 images, and we had to increase the data set because this is a very small, what you can say, part or a small part of actual data set that any AI algorithm needs. So we actually scale this data set to 40K by applying different augmentations. Basically, we have listed out those over here. Like we applied blur, we applied noise, contrast, brightness level, etc. Other than this, to improve its accuracy to more real data, we actually happen to capture data, barcode data, even from the board camera. So additional data set was actually generated with the cameras that are supplied with the boards. And we also had our own scripts developed because we were actually trying to do multiple barcode detections. We had to detect barcode at a greater distance, so we actually had developed custom scripts to generate a different category of data which is not available in open source, so that we can actually build our solution. So once you have this data set, the next stage that we move on to is the model training. Like previously highlighted, any normal training would work on a CPU, but if you are building a AI model for edge devices and boards, basically you need to have models that are small in size, but they don't lose the performance. So basically, you need models that are quantized in nature. So as previously told by Shripal, we support both post quantization, post training quantization, as well as we support quantization aware training. So for our solution for barcode detection, we actually did quantization aware training, and all the functions that are support functions that are needed to achieve these are provided in the reference model source code. So you don't have to look out or you don't have to code everything by yourself. Okay. Now, even after this variant of training, post quantization and quantization, there is another variant, which is actually the strategy of how you want to quantize, which also Shripad covered in his slide. But here we have two types of quantization in that nature, like fixed type quantization. So these are where your step size is fixed. So we actually support an 8-bit signed, unsigned, fixed type, and we have actually a predetermined range for all the neural network components or layers that we use. So for input and activation data, we basically use a range of 0 to 2, and for convolution and dense layer weights, the quantization range is 0. Minus 0.5 to plus 0.5. Now both are models that we selected, that MobileNet V1 and YOLO V5. They have undergone quantization aware training with a fixed type quantization. Okay. Now, if you see post quantization, sorry, yeah. Now, if you see the weights of these quantized models, for quantized mobile net, we have 693 KB, and for quantized YOLO, it's 6 MB. But if you actually, these are the sizes post quantization aware training. If I had not done any quantization aware training, the size of this models would have been 4 times. So the YOLO model will actually be close to around 24 MB, whereas the mobile net V size will be 4 times of this, close to around 3 MB, I guess. Okay. So yeah, quantization aware training is necessary, and we do recommend them in our design methodology, as well as they are part of a reference model source code. Now we are planning to support a new type of quantization, which is learned step quantization, and you will be able to see this in upcoming releases. Okay. Now moving on to after quantization and all, now comes the stage compilation. Now during compilation, you actually have to run your models through the NN compiler, the neural network compiler. Now here, as a part of methodology, what we diligently follow is, once you train a model, you don't spend much of your time into making your train model as accurate as possible and spending most of time in the iterations before compilation, because that is what normally most of the engineers will do. But when you're building it for an edge device that comes with a compiler, this step becomes critical, where what you have to do is, once you create a minimal model, you have to initially run it through evaluation with the NN compiler. So why this is important? Because with a minimal training, you'll be quickly able to identify if your model is having some issues with the compiler. Okay, whether it's going through easily, is there is any problem with the size or the memory. Basically, if you are using a reference models as a base, these problems are very minimal. They will be very minimal. But if you are trying to build your own, then this becomes important, that you first create a model as quickly as possible, run them through compiler, and evaluate it whether what issues are you are facing through the compiler. So that's why we always say that, okay, go in choosing models from the model zoo is very important. Now after you have done evaluation, there are certain features that come with NN compiler that helps you doing this evaluation even better. Now there is a feature called as USB debugging. Now once you have this model, if you want to test the model's performance on an hardware without the need of that RTL programming, you can actually do that with this feature. So this feature actually allows you to test your model without the hardware. Now, this is a very good feature, and we have diligently relied on this feature, because these hardwares are very, what you can say, very, you don't have to always spend time on plugging, flashing devices, and programming them with the MCS file and everything. Uh, and then come to a stage, okay, my model is working better. But this USB debugging feature actually saves a lot of time in that. So now, once you actually, I will recommend everyone to use this feature. Okay. Now, this USB debugging not only provides just a performance, but it also provides some important logs that you can actually use to do a very initial level of evaluation. For example, using debugging, you can actually get the output of the last layer of the model, and you can actually compare them whether they perform better on the hardware as they were performing better on your GPU when you were actually training them. So this is what we call as a mean average error. So the average mean error we have shown for the two models that we have trained here are in the table. Like for MobileNet V1, we had uh, mean average error of 0.01, and for ULUIFI which we have a 0.022. So this is very, very low. Okay. Also, it provides you cycles which you can use to calculate FPS. So without using the hardware, we are actually able to calculate at what will be the FPS of this application once it goes on the board. So for MobileNet V1, the calculated FPS came to 90 FPS, and for YOLO V5 it was 10. So yeah, this compiler with its features is a very powerful tool in the sensAI stack that helps you evaluate your models without actually having the boards with you. Yeah, and yeah, like I said, the compiler logs provide you vital information on cycle consumptions and memory locations. Now, this you can effectively use to even select your devices at the later stage. You don't have to actually determine, okay, what device will be useful for your application. You can quickly start with your problem statement, build the AI model. Okay, once you are at the compiler, at that stage point of time, you can select and decide which device you want to go ahead with. So this compiler comes with a drop down of all the FPGA boards that we have at our Lattice ecosystem, and you can actually select one of them, go through the compilation, and retrieve the performance of the model. So this table gives you a summary of how our two models performed on different hardware. So for Crosslink NX, the cycle count, YOLO V5 is actually not supported on Crosslink NX since it's on optimized CNN IP. But Certus Pro, we got those cycle count. Now, if you see over here, these are the mobile net V1 is actually performing faster compared to YOLO V5 because the cycle count is small. So that's why we selected Certus Pro NX with advanced IP for our application, and it also gives us an advantage that okay, if we want to do something on YOLO, we'll be able to do that. Okay, so now finally, once you have the model, you have decided, you have also selected your device. Now the important thing is testing. Now testing of the model you can do with the help of score MAP scores that we have provided with the reference model. So the MAP score is actually a evaluation metric for models on that are built on object detection. So every problem statement, every AI problem statement has a evaluation metric. For classification, we have confusion matrix. So for object detection, we have MAP. So there is already a script provided in the reference model that you can use for evaluating your models once it is trained. If you are not satisfied with this score, okay, you can definitely add your own metrics and determine which model is best. And yeah, we do have certain models that come with custom metrics like B-box loss, confidence loss, even probability loss. So the way you want to determine which model works best for you, you can always go ahead with that. Okay, now finally we want to go the last stage, that is deployment. So all these reference models, they come with RTL design code for quick deployment. So you don't have to necessarily do all the RTL design and coding of the models to be deployed. The reference design comes with all the blocks that are necessary, like image resizing, non-maximum suppression, grayscale, and all. Okay, and these reference design also come with the Radiant project workspace. So if any user wants to do custom modifications to this pipeline to enable some new cameras or some other sensors, they can definitely use this project workspace for modifications. Okay, and with this, yeah. So coming out to the last stage, so our overall solution, while we were going through all the stages, we saw that we were working with two different models. So now how we end up to a final solution. So this table gives you a summary on that. So the algorithms that we experimented with were two: YOLO V5, MobileNet V1. Okay, our final model that we selected was MobileNet V1 because it performed better in terms of performance and it gave us our expected accuracy that we wanted. Okay. The dataset size overall we created using custom open source that was close to 150K images. Okay, the barcode dimensions that we worked with was basically 5 centimeter cross 4 centimeter to 11 centimeter cross 5 centimeter. Okay, the number of models that we trained before we came to a final is almost 8 models. Okay, we also took how far our model will detect barcode. So the maximum distance that we achieved for barcode detection was 250 centimeter, and the minimum distance is 40 centimeter. Now, on the right hand side, you can see the RTS solution, which was basically with what FPS it performed, what is the inference time, stable speed detection, and all. Okay. So yeah, MobileNet V1 was a clear winner for us in our solution.
So let's move on to demo, Rakesh.
Yeah.
Thanks, Rakesh, for a very nice presentation as well as a demo. Definitely, this is a very good reference design for our customers to develop a lot more application on top of it, kind of thing. So here is the summary, overall summary. So Lattice basically provides a very good flexible solutions, right? So it has flexibility in terms of
Right, right,
engine selection. It has flexibility in terms of the flow, and it has in terms of model zoo, for example, reference designs. So it has quite a bit of capabilities and a reference point for enable the customer as a starting point and develop the solution on top of it.
correct,
And just not the flexibility, it also provides a right trade-off between various things like cost versus performance versus. So it's not necessarily like as we saw in the Rakesh presentation, not necessarily the state of the art models are good for all application, right? So sometimes yes, everyone hears about YOLO v5. So jumping onto YOLO v5 may not be the right thing for a given application or given requirement. So there has to be some kind of a trade-off, right? So that's where all the things that we provide as a reference thing act as a good starting point and kind of comparison, rather than user starting or customer starting from scratch on all these models and trying to do something kind of a thing, right? So that's one of the things we learned. And hope you all enjoyed our presentation. And we will go to the Q&A. We ran out of time a little bit, and hopefully we'll be able to take up few questions now. And anything that we cannot address today, we will try to reach out to you directly and give you some more insight into our solution. With that, let's go to Q&A. Okay, I have the first question coming here, basically asking uh, how complex is your solution for a software engineer, like without any expertise in RTL development, to use it, kind of thing. Right? So, very good question. Actually, that's one of the key aspect we always consider in creating this solution and the design methodology. As I mentioned, like we user need not have to know about any of the details of the underlying hardware and things like that. It is kind of abstracted from the user. They can focus only on model training and taking through the compiler to close the loop, because the compiler gives all the required details, information to close on the model, kind of a thing. So we provide a reference designs that basically enables easy downloading of the trained inferencing runtime and things like that. Little bit of hardware knowledge helps at that time. Normally in a company these are all taken care by a different set of a team or a people. They do not have to have ML background. It's a very straightforward things for them, right? And nevertheless, like USB debugging, for example, what Rakesh introduced, it's a very useful feature. Yes, you just need to hook up the USB to your laptop or desktop, and then start using our board. That gives a very good, so not much knowledge is required there. Also, it's like any other embedded device, programming and using the things. And that's where we kind of try to create value for our customer, kind of thing, right? So good question. Okay, so next question, Rakesh, would you like to take the next question?
yeah, sure. I have a next question over here, and the question is like, was open source data set gathered enough to get decent accuracy on performance? Okay, yeah, that's a good question on data engineering. Yeah, data sets are actually fuel for any AI algorithm, and just always the open source data sets are not enough for accuracy and performance. See, we always assume that okay, having more and more of data would be beneficial, but you don't actually get that data. So we too at our end had to generate custom data. We had scripts, we had augmentation stuffs coming into picture, and that's how we got to a figure of 150K images, which we found sufficient enough Okay, and once we trained that model, the results that we got, then we were what you can say, and then we were happy that okay, we achieved a data set, and this data set helped us achieve the accuracy that we desired. So always just relying on the open source data set won't be beneficial. In fact, in certain scenarios, in our case, we actually took like I mentioned, we took images from the camera itself to give it the real more real time images to for the model to understand and come to a good accuracy. Okay.
Thanks,
Yeah.
Rakesh.
Yes,
Yeah.
Shiva, if you
Next
want to
question
like,
is around the power consumption kind of a thing. What kind of power usage we can expect out of your solution? So that is a good question. Again, it depends on a lot of different factors because we don't ship just one device, right? So Lattice provides multiple FPGA devices, each having a different LUT size and kind of things like that, right? So it's a different kind of thing, but we are like in the like a milliwatt range to a watt, less than a watt, right? So on our mid-size FPGA, right? So most of the one the YOLO V5 application that like a model that Rakesh was talking earlier is less than a watt, right? So power wise, that's why we are very competitive compared to any other solution out there. Now in terms of again the performance, we always like to talk in terms of the frame rates and things like that. Rakesh did share some of the frame rates. Again, those are not necessarily right depiction of what you can get out of our solution. So because there are like it depends again on the model size and things like that, the frame rate. But what we try to do is try to see what is the application requirement, okay, whether that frame rate is it required for certain class of application, what is that target, right? So then based on that we try to customize the engine, right? So basically the number of the accelerator and things like that can be customized. So it's the other way of looking at the thing, like look at the target, what is the need, and then try to customize the solution so that you get the best out of all possibilities, right? So that's how we kind of look at this rather than just going with one number and saying that this is what we get, kind of a thing. Yeah, good. Okay, so again, the next one is for you, Rakesh.
yeah, the next question is why do you choose MobileNet V1 as foreigner model when YOLO architecture is state of the art? Oh, okay. I think what Rishipada right now covered was the same that definitely the model that you need is state of the art might not actually work for you. So in our case, what mobile VNet achieved was a better FPS that we wanted, and also the problem statement. If you look at it, it was very simple. So it's just a single flash model detection. It's just a barcode, okay. But if I had to do multiple objects, like okay, other than barcode, I have to detect a person, I had to detect a box, and also I had to detect something else. So like if I want to detect 2 to 3 objects in a particular image, then definitely mobile VNet would not have been my choice. Okay, definitely in that case, YOLO V5 would have actually performed better. Okay, so depending upon the problem statement, so if the problem statement is simple, you should always try to keep your solutions also simple. And if the problem and then if the complexity increases, definitely you might have to increase the complexity of the algorithm itself also. Okay, so now for us, mobile VNet was clear winner because of higher FPS. It got similar accuracy of YOLO V5, and also the prime important thing that we were looking for was whether it detects barcode in motion. So that's where both were able to detect, but the mobile VNet was actually detecting barcodes at a pretty higher rate. Okay, quickly compared to YOLO V5. So that's why we ended up selecting mobile VNet. MobileNet V1 version. Yeah.
Thanks, Rakesh. So we have a few more questions,
Yeah.
but unfortunately, we ran out of time for today, and definitely we try to reach out to some of you with answers, or you'll find a lot of these things already addressed in our user guides and a lot of literature that are available online at Lattice website. Again, thanks for joining the developer conference, and hope you will enjoy the rest of the conference and our presentations. And feel free always to reach out for more information. Thanks again. Thanks, Rakesh.